So when we last left off, we were looking, let me find the pen, one moment. There we go. So when we last left off, we were looking at the overall hybridization and atomic orbital overlaps found in formaldehyde. In this case, in formaldehyde, we have a carbon-oxygen double bond. And as we discussed last class session, a double bond is really composed of two unique types of orbital overlap. The first of which is our sigma bond, which is known as our single bond orbital overlap. And then our double and triple bonds. So this second bond shared between carbon and oxygen, what do we call that double or triple bond? What? Pi bond, exactly. Okay. Now, thinking about the hybridization of carbon, it's sp2 hybridized, so that's why we have 3 half-filled hybrid orbital, and we have an unhybridized p orbital. Again, we promoted this electron to facilitate formation of chemical bonds, to allow half-filled orbitals that are capable of overlapping to form bonds. Now, if we take a special look at this oxygen atom, is this oxygen atom hybridized? Are we dealing with hybrid orbitals or atomic orbitals? Atomic orbitals. So this oxygen is unhybridized. And this is a really important point to keep in mind. Why do we make hybrid orbitals? What is the driving force behind generating a hybrid orbital? What are we trying to do? We're trying to maximize bonding. We're trying to generate half-filled orbitals that are capable of forming the required number of chemical bonds. And if we take a look at oxygen, how many bonds is oxygen forming with carbon? 2. So how many half-filled orbitals do we need? 2. And let's get a little bit more specific here. One of these 2 p orbitals can be used, so p orbitals can be used to form both sigma and pi bonds, depending on their arrangement in 3D space. So one of these p orbitals we're going to use to form a pi bond. The second of these half-filled p orbitals are going to be used to form a sigma bond. Okay? Now, you may ask, and you may notice, oxygen has 2 lone pairs, otherwise known as non-bonding electrons. Do we observe 2 lone pairs in our atomic orbitals? Do we observe 2 pairs of electrons in our atomic orbitals? Yes. Yes. So are these 2 full orbitals holding our lone pairs that we see in oxygen? Yes. And let's just label that for completeness. These 2 are full non-bonding orbitals. So does that make a little bit more sense as to why the oxygen is not hybridized? It does not need to hybridize in order to maximize bonding. There's no energetic benefit, and you won't necessarily end up with your electrons in lower energy orbitals, nor would you be able to form additional bonds if you chose to hybridize oxygen. Again, I would just want to emphasize this idea of hybridization and orbital overlap are tools to explain the observed chemical bonding features in our molecule. So let's look again at our orbital picture, and let's just talk a little bit about each of the orbital overlaps. So looking at formaldehyde, as our carbon is adopting an sp2 hybridization, let's label these hybrid orbitals so that we can get a little bit more detail. So what are each of these hybrid orbitals that carbon is using for bonding? What hybrid orbitals are they? What's the hybridization? sp2, exactly. So this carbon, as it's sp2 hybridized, has 3 sp2 hybrid orbitals that it uses for chemical bonding. And it's using these hybrid orbitals to form sigma bonds. That's why we have a total of 3 sp2 orbitals. So how many single bonds do we see attached to carbon? 3. 1, 2, 3. Okay. Labeling the orbitals that hydrogen is using as part of these carbon-hydrogen single bonds. What orbital is hydrogen using for chemical bonding? Yep, it's an atomic orbital. It's a hydrogen 1s orbital. Perfect. Now, because carbon has an sp2 hybridization, this carbon has a leftover p orbital. And that leftover p orbital is going to be used to form a pi bond. So the first orbital being used in this pi bond is a carbon 2p orbital. And then what orbital is oxygen contributing to form a pi bond? A pi bond is an overlap between what kind of orbital? P orbital. Yeah. So what orbital is oxygen contributing? A p orbital. More specifically, an oxygen 2p orbital. Okay, so far so good. And just to make this abundantly clear, when we look at the carbon-oxygen single bond, what orbital is the oxygen atom using to form a sigma bond, to form a single bond? A p orbital. Yep. So this is a sigma carbon sp2 plus oxygen 2p. And the reason why I like to indicate my orbital n value is, does that orbital n affect the size of my p orbital? Yes. If this was a 3p orbital, for example, in sulfur, the orbital would be larger. It also affects the energy. Okay. Now, an important and a key feature, due to the fact that we have a pi bond, due to the fact that we have a double bond, is that this double bond and this pi bond constrains how readily we can rotate the sigma bonds found in this molecule. This pi bond locks our molecule in a planar orientation. So this locks our carbon-oxygen bond. Now you may ask, why can't I rotate these? Why can't I rotate my carbon about the carbon-oxygen bond axis? Well, if I tried to start to rotate my carbon and only rotate my carbon, what would happen to this pi bond? What would happen to this orbital overlap? It would break, exactly. This is often why double bonds are considered conformationally constrained. They can't rotate about the double bond because you have this orbital overlap that if you attempt to rotate your carbon, you'd be breaking this bond and breaking this orbital overlap. And breaking bonds in general is highly disfavored unless you're forming new chemical bonds. Does that make sense, Sarah? Okay, let's talk about the next major, and let's really take a look at one of the other implications of hybridization. So let's look at the molecule CH2NH. So CH2NH. Now, let's try to describe the location of the electrons and the orbitals used for bonding in this molecule. So let's start by drawing a Lewis structure to give us a sense of things. So following our condensed structure notation, what's the first motif that we should draw? CH2. Yep, CH2. So let's draw that. So we have a carbon with 2 hydrogens attached. And attached to that carbon, what motif should we draw? Yep, a nitrogen with a hydrogen attached. Okay. Now, if we count electrons, we can fill in this structure with the exact number of lone pairs and double and or triple bonds. So carbon contributes 4 electrons. These hydrogens contribute a total of 3 electrons, and nitrogen contributes 5 electrons. So adding these up, we have 12 electrons in this structure to work with, and we formed a total of 1, 2, 3, 4 bonds. So we've used up 8 electrons, and we have 4 electrons remaining. if we want to fulfill the octet of all atoms in our molecule, where are we going to place our lone pairs first? Nitrogen, exactly right. So let's do just that. And nitrogen, considering it currently only has 4 electrons to its name, how many lone pair electrons does it need? Well, 2 lone pairs, 4 lone pair electrons. Yep. The logic is perfect there. Okay. Now, is carbon very happy with this arrangement? No. So we're going to convert one of our lone pairs on nitrogen into a double bond. So we've used up all of our electrons, and we have a structure that now fulfills the octet rule. Everyone okay so far here? Okay. Now, let's now identify, and let's try to identify the hybridization of each of these central atoms. So, considering this carbon is forming how many single bonds? How many sigma bonds is it forming? 3. And it's also forming a pi bond. So what hybridization do we need to adopt to form 3 single bonds? sp2. So this carbon is sp2. Okay. Let's look at this nitrogen now. This nitrogen has 2 bonds and it has 1 lone pair. So to hold these 3 unique charge spheres, what hybridization do we need to adopt? sp2. Okay, perfect. Let's now start to draw a rudimentary orbital picture here. So I'm going to draw our skeleton, and then we're going to flesh out our skeleton. Okay, so here's our skeleton in place. Here's our skeleton in place. And since carbon, we've established this carbon is an sp2 carbon, and this nitrogen is an sp2 nitrogen. Okay, so what orbitals is carbon going to use to form single bonds? What orbitals is carbon? What was that? Form the single bonds?
Oh.
Just the sp2 hybrid orbitals. The reason why we hybridize is to generate half-filled orbitals that are capable of bonding. So let's draw out our sp2 orbitals. Okay, so these are our carbon sp2 orbitals. Okay? Likewise, if nitrogen is sp2 hybridized, what orbitals is it going to use to form single bonds, sigma bonds? sp2, exactly. So let's draw that out using a slightly different color. So this is a nitrogen sp2. Now, nitrogen is going to use 2 of its sp2 orbitals for bonding. What about its 3rd sp2 orbital? Nitrogen has a lone pair, right? So where is that lone pair going to be? Yep, in that sp2 orbital. So the key feature of this molecule that I want to bring to your attention is this lone pair is in an sp2 orbital. Okay, to round out this picture, we have established and we've formed a carbon-nitrogen single bond. So this is our sigma bond. So let's label it as such. Let's label it as such. So this is a sigma carbon sp2 plus nitrogen sp2. Perfect. So we've described the single bond between carbon and nitrogen. Now, what orbital overlap is responsible for our double bond? The double bond, a pi bond, is an overlap of what orbitals?
P orbitals.
P orbitals, exactly. So let's draw our p orbitals. And I'm going to draw my pi bond as a set of lines between our p orbitals. So let me phase them to be 100% correct here. There we go. So this interaction between our p orbitals, this overlap between our p orbitals results in our pi bond, which is between our carbon 2p and our nitrogen 2p orbitals. Does that make sense to everyone? Any questions on the picture that we've drawn so far? Yes.
So when we draw the p-bonds, was the shading to show that they are pi bonds?
The shading indicates the phase, and it's respecting the fact that p orbitals have phase, and essentially in order for you to get a productive pi bond, two regions of the same phase must overlap. We'll talk more about that in a moment in lecture.
And should we be drawing them longer than the sp2s?
Yes, yes. Okay, so to round out this discussion, what orbitals are the hydrogen atoms using? S. Yes, more specifically the 1s, but it's very, very important that you noted that they are unhybridized atomic orbitals. So if we were to label this bonding interaction, whoops, let me zoom in. If we were to label this bonding interaction between carbon and hydrogen, since it's a single bond, what do we call single bonds? Sigma. Yep. So this is sigma. And what orbital is hydrogen contributing? We said it has the 1s orbital. So what orbital is hydrogen contributing? Yep. It's contributing a hydrogen 1s. And then what orbital is carbon contributing to this bond? sp2. Yep. Okay. Now let's take a step back. Why am I having you do this? Thinking about this lone pair, is the fact that it's in an sp2 orbital important to consider? Does the orbital that a lone pair is located in affect its energy?
Yes.
Yes. So then, whenever you look at a molecule, I want you to identify each atom's hybridization, and I like you always to think, where are my lone pairs located? What is their energy? And that's based on the orbital that the lone pair is located in. Does that make sense to everyone? Okay. So this kind of analysis is the stuff that you'll do throughout this class, and I just want you to get comfortable identifying what orbitals are used for bonding, because that has a critical importance in determining bond length and strength. And we'll talk about that next in a few moments. Any questions on this orbital picture? Okay, let's keep going then. We'll draw a few more of these pictures. So we're going to take a short detour next and talk a little bit about structures known as incomplete octet structures. These are very closely related to our discussion of the sp2 hybridization. You primarily see incomplete octet structures with aluminum and boron. So aluminum and boron are your typical culprits in incomplete octet structures that you'll see in this class. As their name implies, they form structures with less than 8 electrons surrounding the central atom. Now, the key feature of many incomplete octet structures is that they will have an empty p orbital that is not utilized for bonding or to hold lone pairs. So just remember this idea of an empty p orbital, and we'll draw it out in a moment. The reason why this is so important, and the reason why we often use aluminum and boron containing reagents in organic chemistry, is that chemical species with empty p orbitals have unique reactivity and are known as Lewis acids due to their ability to coordinate and interact with lone pairs. We'll elaborate on Lewis acids in more detail in a later chapter. So let's take a look at AlCl3, or aluminum trichloride. And let's try to draw a valid Lewis structure for aluminum trichloride. And let's try to identify the hybridization of our central atom. So first and foremost, let's take a moment and let's count our electrons. How many electrons does aluminum contribute if aluminum is a 3A element? 3. Okay. Chlorine as a 7A element contributes how many electrons? 7. 7 times 3 gives us a total of 24 electrons. So 21 plus 3 is 24. What would be our central atom? What's the least electronegative non-hydrogen atom? Aluminum. Yep, it's okay. So let's put aluminum in the center. We're going to surround it with each of our chlorine atoms. Okay, I'm going to put my chlorine atom here just to make things easier for the next step. Then we're going to form one bond each. 1, 2, 3. So that uses up 6 electrons. We have 18 electrons remaining. Where do we start placing our 18 electrons? Chlorines. Yep, exactly. So 2, 4, 6, 8, 10, 12, 14, 16, 18. We've used up all 18 of our electrons. Now, you may say, why don't I form a double bond to give aluminum a complete octet? Well, let's try that. Let's try that. So let's suppose that we write out a structure for aluminum trichloride that contains an aluminum chlorine double bond. Now, in 101 or 102, this would be perfectly A-okay. There wouldn't be any major issues with proposing this structure. However, considering our exposure and our knowledge of formal charges, would anyone like to take a guess why this structure in red has an issue? Why this structure is not as favored as the incomplete octet structure? Formal charges. Yeah, this structure in red has a formal charge of -1 on aluminum. Where did we get -1 from? Calculating formal charges, let me break out a different color. Aluminum has a group number of 3, and it has 4 bonds to it, leading to a formal charge of -1. Okay? That's not as egregious as the offense of giving chlorine a formal charge of +1. Now, does chlorine prefer to have positive or negative formal charges? Negative. So giving a positive formal charge to chlorine, that does not seem very favorable. So even though the structure on the left in red follows the octet rule, it does not adequately describe the actual bonding arrangement for aluminum trichloride, or AlCl3. Now, taking a look at the correct structure for aluminum trichloride with 0 formal charges, if we had to just count the number of bonds that aluminum is forming, how many bonds is aluminum forming? 3. So let's take a look at aluminum's orbital diagram. Let's take a look at aluminum's orbital diagram. So aluminum is in the 3rd row. So we have the 3s and our 3p orbitals. So our 3s is completely full, and our 3p orbital has 1 electron. Now, clearly we can't form these 3 bonds just using our atomic orbitals, right? Do we have enough half-filled orbitals to form 3 bonds? No, we can only really form 1 if we're just using the atomic orbital model. However, if we presume that aluminum can hybridize, considering how many single bonds aluminum has formed, what would the hybridization, theoretically, of aluminum be? sp2. Yes. Yes, because, and let's talk about that actually. If we zoom in on the periodic table, what row is aluminum found in the periodic table? The 3rd, yeah. So that's why instead of a 2s and 2p as when we were discussing oxygen, it's the 3s and 3p. Now, the critical feature and the reason why aluminum trichloride is able to function as a Lewis acid is if this aluminum is sp2, in the sp2 hybridization, what do we have left over? What do we have available? Beyond a p orbital. Exactly. So sitting on this aluminum atom is an empty p orbital. And more specifically, it's an empty 3p orbital. And this empty p orbital can engage and coordinate and interact with lone pairs. So anytime you see this stereotypical empty p orbital, no lone pairs, that's a sign you're dealing with what's known as a Lewis acid. Does that make sense to everyone? Yes.
So the other orbital is also empty.
Which one?
The one on the bottom.
Ah, this whole thing is one p orbital, because remember, p orbitals are dumbbell shaped. Yes, but that's a very important point to make. This whole thing, above and below the aluminum, is one p orbital. Yes?
So how would you write out the hybridization using the electron configuration of the 3s?
Ah, yes. So let's showcase that. So if we wanted to hybridize aluminum, we generate a total of 3 hybrid orbitals and 1 unhybridized 3p orbital. We then take our 3 electrons and assign 1 electron each to our hybrid orbitals. And the reason why we place these electrons in our hybrid orbitals is because we are using them to form sigma bonds, single bonds. Does that make sense to everyone? Any other questions on this example? Okay. So let's try to look at a few more examples, and let's try to practice drawing a few additional orbital pictures for other hybridizations. The last major hybridization that we observe in the organic chemistry class is the sp hybridization. As its name implies, how many s orbitals are we combining? 1. So we're taking 1 s orbital and we're combining it with how many p orbitals? 1. Okay, so if we put 2 orbitals in, how many orbitals do we get out? 2. So we have, oh, one moment. 1 and 2. And always keep in mind, what is left over? What have we not hybridized? What 2 orbitals have we not hybridized? The p orbitals, exactly. So let's draw them out. So we have, in addition to our 2 hybrid orbitals, we have a p orbital and a second p orbital. Notice how I'm, one moment, let me actually draw these with proper phasing to emphasize this point. Notice how these p orbitals, do they have the same or different 3D orientation? Different. So then, both of these p orbitals can be used for pi bonds, but will those pi bonds be exactly the same orientation in 3D space? No, they'll be in different orientations. Okay, so as we have 2 p orbitals, how many pi bonds can an sp hybridized atom make? 2, exactly. Okay, now, remembering this idea that hybrid orbitals have an energy based on the 2 or more orbitals that you use to make the hybrid orbitals, if we have less p character and more s character, we have more low energy, short orbital character, what would we expect our sp hybrid orbitals to look like? Would you expect them to be high in energy or low in energy? Low, yep. So these sp hybrid orbitals are low energy. And would we expect them to be long like a p orbital or really, really short and stubby? Short and stubby. And this is important because these little short, fat hybrid orbitals, so these are short and stubby, This affects, since bonding is an orbital overlap, this has a direct impact on our bond length. This overlap is closer to our nucleus because we have a shorter orbital. Does that make sense to everyone? So always think, what do my orbitals look like? What is their energy? Yes.
It's closer to the nucleus.
Yes, because the orbital itself, like an S, is shorter and more withdrawn, closer to the nucleus. That's part of the reason why it's lower in energy. So let's talk a little bit and let's try to draw some sample orbital pictures, and let's try to understand how the sp hybridization relates to molecular shape. So the sp hybridization applies to an atom with 2 electron groups. This corresponds to the linear electron pair geometry. In other words, when you observe a geometry with 180-degree bond angles between your atoms, you're dealing with an sp hybridization. There's 180-degree separation between our hybrid orbitals. Now, as we've discussed earlier, sp orbitals are the shortest and lowest energy hybrid orbitals. Okay, so from these orbitals, we'll generally form short, low energy bonds, right? The orbitals that you use for bonding directly impacts the nature of your bond. So let's take a look at a picture. Let's take a look at a picture, as this is really what the meat of this discussion in this class is. So looking at carbon, again, let's always start with our baseline atomic orbitals. Let's always start with our baseline here. Carbon, as we discussed, has how many valence electrons? How many valence electrons? 4. 1, 2, 3, 4. Okay. So in C2H2, which looks a little bit like this, our carbon atom needs to form how many single bonds? How many single bonds are surrounding this carbon atom? 2. 2 single bonds. So how many half-filled hybrid orbitals do I need? 2. Okay. So this carbon atom needs to form 2 sigma bonds, and this is part of the reason why this carbon hybridizes, how many double bonds or triple bonds? How many pi bonds does this form? 2. Okay, so we have our marching orders. I need 2 half-filled orbitals, and to form these pi bonds, I need 2 half-filled what kind of orbital? P orbital, right? Because for pi bonds, these are based on what orbital overlap? The pi bonds are based on P. Yes. Okay, so this is the reason, and this is part of the reason why our carbon is hybridizing at all. Because it not only needs to have 2 hybrid orbitals for bonding, it also needs 2 half-filled p orbitals to form the double and triple bond. Yes?
So I know the difference between an s orbital and a p orbital.
Yes.
Right? But I'm like, we only call it sp when they are
Mixed together and hybridized to make a new hybrid orbital.
right. So when you just said which orbitals do you need to bond with the hydrogen? Can you call that sp? Because it's
Yes.
bonded
So
up
you're
like
using an sp hybrid orbital,
that? Yeah.
and the orbital that hydrogen contributes is an s orbital.
Right.
And that overlap makes a molecular orbital.
Okay.
Does that make sense?
Yeah.
So let's hybridize this carbon according to the sp hybridization. So we're going to take an s orbital and a single p orbital, and we're going to mix both their shape and relative energy. So we have 2 p orbitals just unhybridized. And the remaining 2 orbitals are our hybrid sp orbitals. They're lower in energy than a typical p orbital and slightly higher in energy than an s orbital. Everyone okay so far with this picture? Now we have 4 electrons to work with, so are we going to fill these orbitals with our 4 electrons? Yes. So let's do just that. So I'm going to place my first 2 electrons in my low energy sp orbitals. Now, if we want to maximize bonding, can we place our electrons in higher energy orbitals if we're going to form some bonds? Yes. Okay, perfect. So now, based on this orbital diagram, after hybridization, we're going to have a total of 2 half-filled p orbitals with different orientations and 2 hybrid orbitals with a relative geometry of 180 degree angle between our 2 hybrid orbitals. This is one sp, this is the second sp orbital. And do you notice how they're directly 180 degrees apart from each other? So that's why the sp hybridization correlates with a linear geometry, correlates with 180 degree bond angles. So based on the bond angles and geometry we observe, that gives us a tool to help rationalize and explain the hybridization of the atoms in our molecule. Okay, so let's talk a little bit about these p orbitals, as this is really important. The fact that these p orbitals have different 3D shapes is critical. So let's take a moment and let's draw that out. So between our 2 carbon atoms, if these 2 carbon atoms are both sp hybridized, let's draw our hydrogen atoms. If both of our carbon atoms are sp hybridized, if we want to form our carbon-carbon single bond, are we going to overlap these sp orbitals? What are sigma bonds are formed by the overlap of what kind of orbitals, typically? Sp, hybrid, or atomic. So our first carbon-carbon single bond is going to be formed by overlapping our 2 carbon sp orbitals. So we call this a sigma carbon sp plus carbon sp. Okay? We can also form a single bond with hydrogen's atomic orbital. Let me change the color for that. And in this case, what would we label this sigma bond? What would we label this carbon-hydrogen single bond? Is it a single bond? Is it a sigma bond? So we write it as sigma. And what orbital is hydrogen contributing? 1s, yep. And then what orbital is carbon contributing? Yep, exactly right. Exactly right. Does that make sense to everyone? Does this look, are we starting to get the hang of identifying what orbital overlap is responsible for each type of bond? Now, let's address our p orbitals. And I'm going to clear up a little bit of space here, just so that way we can fully address these p orbitals. So the p orbitals have different orientations in 3D space. So let's draw our first set of p orbitals that are going to be vertically above our bond axis. Okay, so this is one of our 2p's. This is our second 2p orbital. Now, p orbitals have a phase. So if you want to draw a pi bond, you want to show the 2 shaded regions on the same side of your single bond. Essentially, this shading is telling us the orbitals have the correct phase to overlap and actually form a bond. So then, since we have these 2 p orbitals, can we overlap them to form a pi bond? Yeah, so this is going to be our first pi bond. This is going to be a pi carbon 2p plus carbon 2p. Okay, so we have one pi bond occurring above and below the bond axis. Both of these overlaps are one single pi bond. Does that make sense to everyone so far? Okay. Now, our second set of p orbitals, and I'm going to use a slightly different color in orange for this, are going to push out of the page towards us. They're in front of our bond axis. Now, just like before, p orbitals are phased. And since we have another set of p orbitals to work with, can we overlap those p orbitals and form another pi bond? Yes. So this is our second pi bond. This is a pi carbon 2p plus carbon 2p. And the key feature I want you to take away from all of this, what is the criteria for these orbitals to overlap? Do they have to be pointing? Do they have to have the same orientation to overlap? Looking at the picture.
Yes.
Yes, they have to have the same orientation. So when we get to what are known as pi systems, when we start talking about resonance, I always want you to keep in mind, we can only overlap our p orbitals to form pi bonds if the p orbitals have the same orientation. Does that make sense to everyone? So when you look at sp hybridized atoms, they have one pi bond occurring on the vertical axis and a second pi bond on the horizontal axis. Okay. We will see pictures like this again when we, yes.
So on the second one you drew, do we not
Yes.
connect the top?
Ah, yes. Yes. I was trying to avoid having the drawing be too crowded. Yeah. But yes, both lobes of our p orbitals are overlapping. Okay. So, as we can see from this overall picture, when we look at triple bonds, they're relatively hard to break as a result of this large amount of electron density shared between our atoms. Okay. Any questions on this orbital picture? So we've covered all the major orbital pictures and hybridizations that you'll see in this course. What we're now going to do is we're going to start to assess molecular geometry, and we're going to start to draw Lewis structures and assign and draw orbital pictures for those Lewis structures. So let's take a moment and let's look at quite an infamous molecule, hydrogen cyanide, HCN. What I want you to do for hydrogen cyanide is I want you to draw a Lewis structure for hydrogen cyanide, and then I want you to draw an orbital picture of all of the bonds in hydrogen cyanide. And the key question I want you to answer for me is, where is the nitrogen lone pair? Any questions so far? Looks good so far. Just draw all the orbitals on there. Everything drawn up. Your Lewis structure looks good. And teacher will draw all the orbitals on carbon and nitrogen. Any questions so far? Well, so looking at the hybridization, what would the hybridization of both the carbon and nitrogen be? How many single bonds do we see? Yep, so we have 2 single bonds. Yep, exactly. Any questions? Yep. Yep. And now make sure to draw all the orbitals and try to see where does that lone pair end up. Any questions? Yep. All of that 2. Yep. 1 on the right, 1 on the left. And the SP line corresponds to a linear geometry. So you should draw all of your 3 atoms in a straight line. Does that make sense? Good. Any questions? Yes. Oh, SP hybridization. Essentially, because carbon needs to form 2 single bonds, it adopts the sp hybridization. And if we think about the floral sense, that means we have 2 hybrid orbitals and 2 p orbitals that are 2 full forming bonds. Does that make sense? Just like our example we did comparing like methane and ammonia, it follows similar logic. The only difference between carbon and nitrogen is one of our orbitals may end up having something. So we can go back to I see. So so this is unhybridized. Now try hybridizing, you see what happens. Yes. Yes. So what orbital is our lone pair? Yes, it's an SP. Exactly right. Does that make sense? Yes. Perfect. So let's talk a little bit about this example, and let's think a little bit about carbon and nitrogen. So in hydrogen cyanide, everyone was very quick to note and draw out the following Lewis structure for hydrogen cyanide. Wonderful, perfect. Let's now identify the hybridization of each of our 2 atoms. So what would the hybridization of carbon be? SP. The reason why it's SP is how many single bonds, how many sigma bonds are we forming? 2. Okay. Okay, for nitrogen, you may ask, why am I hybridizing nitrogen? Well, let's draw a diagram for nitrogen, and let's see how do the atomic orbitals look. So we have our 2s and 2p. Nitrogen, unlike carbon, unfortunately, has how many electrons to its name? 5. Okay, 1, 2, 3, 4, 5. Okay. So in our structure as drawn, we need to form, nitrogen needs to form how many single bonds? Wait. How many single bonds is nitrogen? 1, yeah. So nitrogen needs to form 1 single bond. Okay, so we have a half-filled orbital for that. And how many double bonds does nitrogen need to form? How many bonds past the single bond does nitrogen? 2. Okay, so let's box those in. Now, it is slightly subjective as to what, whether or not nitrogen will hybridize. If we consider that nitrogen will hybridize, to maximize and favor and form this carbon-nitrogen single bond, let's show what an orbital diagram would look like for nitrogen after it hybridizes. So here's our nitrogen atom after hybridization. We have 2 sp orbitals and 2 half-filled p orbitals. Let's fill those orbitals in with electrons now. And the only thing that changes when we compare carbon and nitrogen is how many electrons does nitrogen have? 5. So what happens when we try filling these 4 orbitals? We end up with one of our orbitals holding what? A lone pair. So this set of electrons in an sp hybrid orbital is a lone pair. And more specifically, it's a non-bonding. Okay. So we have a sense, and we're starting to get a sense for the hybridization of each of the atoms in this molecule. Let's now try to draw an orbital picture using this information. Just as a refresher and just to make sure we're all on the same page, for carbon, if it's sp hybridized, we will have the following orbital arrangement. So we have our sp hybrid orbitals and our p orbitals. If we fill those orbitals with electrons, one moment. Carbon only has 4 electrons, so we have 4 half-filled orbitals ready to go for bonding. Okay. Now that we have our pictures established for our sp hybridized carbon and our sp hybridized nitrogen, let's draw out each of those orbitals. So first things first, I'm going to draw my skeleton. So we have HCN, a hydrogen, carbon, and a nitrogen. To form this carbon-nitrogen bond, to form the first single bond, our first sigma bond, what orbitals are we going to use? Yep, so we're going to use the 2 half-filled sp orbitals. So carbon's going to contribute its sp orbital, and nitrogen will contribute its sp orbital. So if we're going to write this out in full notation, this would be a sigma carbon sp plus nitrogen sp bond. Okay. What is the other sp orbital in nitrogen being used for? Yes. Yes, exactly. And my question to everyone now is, what is the second sp orbital in nitrogen being used for? A lone pair. Exactly, exactly. So this lone pair is in a nitrogen sp orbital. And would you think that would affect the energy of that lone pair? Yes, because by definition, does hybridization of the orbital affect the energy of the electrons in that orbital? Yes. So as we'll see in the acid-base chapter of this course, depending on the hybridization of an atom, the acidity of protons attached to that atom will change. And that's based on the fact that electrons have different stability depending on the hybridization of the orbital they're placed in. Let's finish up this orbital picture. So we've used up both of nitrogen's sp orbitals. Carbon, we've used up one of their sp orbitals. What is the second carbon sp orbital being used for? Bonding with hydrogen, exactly. And my question to all of you now is, what orbital is hydrogen contributing to this bonding event? 1s, exactly right. One moment. Let me change colors so that. So then this would be a sigma bond between a hydrogen 1s plus a carbon sp orbital. Let me zoom a little bit down so that way we can see. And just like this lone pair electrons energy depends on the hybridization of our nitrogen atom, would you expect this carbon-hydrogen bond to be a little bit different in energy compared to the other carbon-hydrogen bonds that we've looked at so far? Yes. Considering that sp orbitals are lower in energy, would you expect this bond, this orbital overlap, to also be relatively low in energy? Yes. Okay, so we're starting to see the connection between hybridization and bond strength. Okay, finally, to complete our picture, let's draw out our p orbitals. So carbon has one leftover p orbital that's occupying the vertical space. Nitrogen also has a p orbital occupying the vertical space. To form our first double bond, can we overlap these p orbitals to form a pi bond? Yeah. So this would be a pi carbon 2p plus nitrogen 2p. Perfect. Now, this is really important. Where do I draw my second set of p orbitals? On the vertical axis or on the horizontal axis? Horizontal. Okay, so let's draw the second set. I'm going to erase this label just so that way we have a little more space to showcase this. And so, to form our second double bond, can we overlap these two p orbitals? Yep, exactly right. Okay. So we've essentially just redrawn our previous structure for C2H2, except we've replaced a carbon with a nitrogen. So you can also draw, just like Lewis structures by analogy, you can also in many cases make orbital diagrams and orbital pictures via analogy. Any questions on this example? Yes?
When drawing the orbital pictures,
yes.
will we require every time to include the labels?
Yes. And the reason why I'm including these labels is when I ask which of these bonds is stronger. If you know the exact orbitals used in bonding, you can in turn get a sense of their energy and in turn estimate the bond strength. So the labels are a tool to help you as well. Yes?
So I don't know if you were kind of already saying this already,
Yeah.
but so the S in the SP is not as strong as two SPs, right?
We'll talk a little, so it's hard to do the comparison between atomic orbitals and hybrid orbitals because it depends on the atom. What we can say is that this overlap between an sp orbital and a hydrogen 1s is lower in energy than if we replace this with an sp2 orbital, for example. Yeah. In general, sp orbitals are the lowest energy hybrid orbitals for the same atom. So now that we've discussed different hybridizations and their effects and their influence on geometry, we're now going to do a deep dive into molecular geometry and molecular shape. Okay. So just as a summary, if you need a reference table, there are two other hybridizations on this table that we will not see a ton of in this class, but I've included for completeness. SP through SP3 are the main hybridizations of our organic molecules. Okay, so let's now start to take a deep dive into, and let's get a little bit more detail into how do orbitals overlap and how do we describe the sigma and sigma star and pi star orbitals. So let's talk a little bit about what do we mean by bonding molecular orbital? What do we mean by anti-bonding molecular orbital? So in MO theory, the main distinction between MO theory and valence bond theory, which is what we've been using so far, is this idea that instead of having localized orbital overlap, which is valence bond theory. In MO theory, we generate a set of molecular orbitals describing electron density in our entire molecule. Now, when we think about orbitals, it's best to think about them from the perspective of waves, since orbitals are describing electron probability using a wave function. And just like waves can interact and overlap, orbitals overlap and interact in a similar fashion. So, for example, if you have two waves, so let's suppose we have a region of positive amplitude and negative amplitude. And we overlap two waves that both have the same amplitude at the same location. So we're overlapping two waves. When the waves are in the same phase, the region of positive amplitude and negative amplitudes are overlapping. We call this constructive interference. We call this constructive interference. Now, if as these two regions are overlapping and they have the same phase, would we expect a larger or a smaller amplitude after we overlap the waves? Larger, yep. So we end up with a larger amplitude. Now, if our waves happen to be out of phase, we have two waves of opposite phase. So we are overlapping regions of opposite phase. We call this process destructive interference. Now, if we overlap regions of opposite phase, would we expect a larger or a smaller amplitude? Smaller. So much so that we may even cancel out our amplitude. So we would have zero amplitude. Now, what does this mean from the perspective of orbitals? What is this amplitude? What is the amplitude of an orbital function? What does that represent? Amplitude. What is that telling us? So if an orbital is representing the probability of an electron being in a general area, being in a region of space, if this amplitude represents electron probability, what happens if we have zero amplitude? We discussed this really early on in the class. Zero amplitude. What does that mean? The amplitude tells us the likelihood an electron is in that region of space. It's a node, exactly right. So zero amplitude is known as a node. And what that means from a practical perspective is that when we have destructive interference and we generate a node, we have no likelihood of finding a significant amount of electron density at that location. We don't have any electron density in that location where destructive interference occurs. Now, we can describe constructive and destructive interference as bonding and anti-bonding interactions. So when we have constructive interference, we form bonding orbitals. When we have destructive interference, we have nodes generated and we have anti-bonding interactions formed. Does that make sense to everyone? Let's now show you some pictures of these interference examples and what bonding and anti-bonding orbitals look like. So, when we observe destructive interference, the key criteria for destructive interference is that our two orbitals have an opposite phase. Right? We have regions of opposite phase. So it's like as if we're overlapping the positive amplitude wave and the negative amplitude wave. And when we bring them together, what happens when these two probabilities overlap? What do we observe? They cancel out. So what do we see? What happens when we have zero amplitude? A node. And does everyone notice how straight down the middle of our molecule, or straight down the middle of our orbital interaction in our molecule, do we see an empty space? Do we see a region of zero electron density? Yes. And we call this a node. So it's an anti-bonding interaction. We're not sharing electron density between our atoms. Instead, each atom is holding its electron density to itself. There's no significant amount of electron density between our atoms. Does that make sense to everyone? That's what anti-bonding is. Now, if our two orbitals have the same phase, they can engage in constructive interference, and this leads to a bonding molecular orbital. Does everyone notice if we look between our two atoms, do we have a lot of electron density projected or a small amount of electron density? A lot. There's shared electron density between atoms. There's shared electron density between atoms. And just to drive this point home, is having electron density between atoms, is forming a bond. Why is forming a bond favorable? Why do we want electron density between our atoms? Lower in energy. And the reason for that is both of our nuclei have a positive charge, right? So is it beneficial to spread our electrons as close as we can to both of these nuclei? Yes. So this is why bonds are stable, because the electrons in our bond are stabilized by the nucleus of each atom. Okay, so let's show some pictures for how s orbitals overlap. So, as a summary for our discussion, we can take our two s orbitals and overlap them, and we generate both a bonding orbital and an anti-bonding orbital. Okay. As we've discussed earlier, the anti-bonding exhibits a clear node. There is no electron density sitting between our two atoms. That's why our anti-bonding is so high in energy, because our electrons are destabilized because they're not being shared between our two atoms. They aren't being able to be stabilized by each of our nuclei as efficiently. Does that make sense to everyone? Anti-bonding is higher in energy, less stable. Okay, let's now really appreciate the point that when we do overlap orbitals to form a bond, we also generate a corresponding anti-bonding orbital. So when we overlap our two orbitals, we get a bonding orbital and an anti-bonding orbital. The anti-bonding orbital still exists, and many chemical reactions will interact with the anti-bonding orbital in order to make or break new bonds. Let's take a look at our p orbitals now as we really start to observe the effect of phasing on whether we see bonding or anti-bonding. So does everyone notice how our p orbitals are shaded? You have often seen me draw p orbitals with one head or one portion of the p orbital shaded in. What I am representing is the phase. So this will be arbitrarily positive phase, and this will be arbitrarily negative phase. This is phase and not charge. I'm not describing charge here. This is describing in our wave function whether it's positively or negatively phased. And the only thing that phase does is influence how our orbitals interact when they overlap. Whether we see constructive bonding interactions or destructive antibonding interactions. Now, I want you to be comfortable drawing the bonding and antibonding orbitals for each of these overlaps. And just get a sense of what do these bonding and antibonding orbitals look like. Again, as with all antibonding orbitals, what do we notice in the middle of our two atoms? What do we see? A node. Okay. Whenever you observe nodes, regions of opposite phase engaging in destructive interference, that's destabilizing. Our electrons would much prefer to sit between our two atoms and be stabilized by both of our nuclei. So, when we form a bond, both of these orbitals are generated. And how we fill these orbitals with electrons determines how our bond behaves in terms of length and strength. Okay, let's now take a look at our p orbital overlaps to give pi and pi star. So as we notice, a typical pi bond is parallel to our bond axis. Looking at our pi star, what do we notice is a key feature again of the pi star, the antibonding orbital? A node. Yep, we see a node smack dab in the center. Why do we see a node? What are we trying to overlap? Are these two regions of the same or opposite phase? Opposite. Okay, good, good. Now, just in terms of spatial location, our sigma antibonding is behind the bonding orbital. Where is the pi star? About where is the pi star? Is it about in the same region of space as our pi bond? Looking at these two, if we put them on top of each other, where is our pi star? Is it also above the bond axis? So let's draw some pictures. Let's draw some pictures. So I have, and I'm looking at a pi bond. So our pi bond is above and below the bond axis, right? That's what we have established from this picture. Where is our pi star? Where is our pi star? Is it also above and below the bond axis?
Yeah.
Yes. But do you notice how it's a little bit at an angle? How it's a little bit tilted? Okay, so let's draw our pi star. It's above and below the bond axis, but it's at a slight angle. And the reason why I bring this up is that you'll discuss, if not at the end of this class, in your second organic class, reactions that involve breaking pi bonds. And the angle of approach is such that you're attacking the pi star. So knowing where these antibonding orbitals lie can help you understand the overall spatial geometry and spatial orientation of chemical reactions. Why do certain reagents approach our molecule from certain angles? And that's because they're trying to interact with these bonding and antibonding orbitals. Does that make sense to everyone? Yes.
And the star indicates.
Yes, exactly right. So the reason why I want you to understand the relative location of these bonding and antibonding orbitals is so one, you can draw valid orbital pictures, and two, so you can help understand and get a sense of how chemical reactions behave later on in this class. So we're just laying a lot of the groundwork and foundational skills that we'll need for later on in this class. Any questions so far? Yes.
So if we were to draw a pi bond there, like if we had two pi bonds, that'd be incorrect. With the, like, would it have to be the other angle? Or is it okay to be on top of where the antibonding?
It's okay. They're occupying
The
same regions of space. Yeah. But just as a side note, the second pi bond wouldn't be on the vertical axis. It would be in the horizontal axis, right? Because if we look at our second pi bond, it's on the horizontal axis, as we did in the orbital pictures of C2H2, right? Perfect. So let's now continue on with molecular orbital theory. Oops. One moment. And let's now continue on with molecular orbital theory. And let's talk a little bit about how MO theory is used to describe chemical bonding. So this should look familiar from your 101 course. The main purpose of invoking MO theory is to get a sense of the relative bond length and strength for a single interaction between two atoms. MO theory gets progressively more complicated to calculate when you look at larger, more complex molecules, but we can utilize and showcase how MO theory is utilized for simple molecules involving two atoms. So, in MO theory, the central premise is we are going to take each of our atomic orbitals. So our S and our P orbitals. In this case, we're taking a nitrogen atom and bonding and showcasing a bonding interaction with a second nitrogen atom. From these atomic orbitals, we are going to overlap our atomic orbitals and we are going to generate molecular orbitals. So these new orbitals that we formed are molecular orbitals. As we have discussed previously, when we overlap our S orbitals, we can form a sigma. This is our bonding. And we also form an anti-bonding orbital. So we have a bonding, and let me use a different color for this, an anti-bonding. Now, once we've taken and formed our overall molecular orbitals, we are going to fill these molecular orbitals with electrons from lowest to highest energy, just like we do for any other orbital diagram, right? Now, based on the number of electrons in our bonding versus anti-bonding orbitals, that tells us about the nature of the bond between these two atoms that we've drawn. Does that overview make sense to everyone? Let's talk next about how we interpret these diagrams. So this is what these diagrams are showcasing. How do we actually interpret them? So, first and foremost, not all of these atomic orbitals are created equal. As we've discussed time and time again, depending on the exact atom and the electronegativity of the atom, you end up with a different orbital energy. And as we found in 101, orbital energy decreases with increasing electronegativity and increasing effective nuclear charge. So for example, if I was looking at an oxygen 2p orbital and I was comparing it to a nitrogen 2p orbital, which of those two orbitals would be higher in energy? Oxygen or nitrogen? Which of those elements is more, which of these elements is nitrogen would be higher in energy? Yes, you're correct. And the reason why nitrogen's 2p orbital is slightly higher in energy is because which element is less electronegative, oxygen or nitrogen?
You said
Less. Yes, so nitrogen's less electronegative, so it's higher in energy. Oxygen is more electronegative, so its 2p orbital is lower in energy. Does that make sense to everyone? Okay. This is partially why, when we discuss in the acid-base chapter, lone pairs are often more stable on more electronegative atoms. Electron energy depends on orbital energy, which depends on the atom containing that orbital. Okay, so a classic example of this, just to showcase, if we compare the orbitals of nitrogen and oxygen, as you notice, are the orbitals for oxygen conspicuously drawn lower in energy? Do you notice how all of the orbital boxes for oxygen are lower in energy? How they're lower on this graph than nitrogen? Yes. And the reason for that is oxygen is more electronegative. So, and this is really going to tie this all together. If we were to compare the energies of both of these 2s electrons, which electrons are lower in energy? The electrons that nitrogen has to its name, or the electrons that oxygen has to its name? Oxygen, yep. These electrons are lower in energy. And if we form bonds, and the bond energy depends on the orbital energy from each of our two atoms, will oxygen in turn form lower energy bonds? If the overlap depends on each of our orbital energies, will oxygen also end up forming lower energy bonds as a consequence? Yes, exactly. So to tie this all together, the atom affects our orbital energy, which in turn affects our bond energy. It affects the energy of our molecular orbitals involved. Let's talk about one last thing before we go, and it's a very quick calculation to help us interpret these molecular orbital diagrams. So, to tie this all together now and to showcase how these bonding and anti-bonding orbitals affect the nature of our chemical bond. Electrons in bonding molecular orbitals are lower in energy. Remember, bonds are stable. Bonds are low in energy. When we talked about anti-bonding molecular orbitals, were they low or high in energy? High. They're high energy. Anti-bonding MOs are high energy. Now, bonding and anti-bonding molecular orbitals are related in that filling a bonding molecular orbital strengthens a bond. You're putting more electron density between your two atoms. However, when you start to filling your anti-bonding molecular orbital weakens your bond. And eventually, if your anti-bonding molecular orbital is completely full, you will break your bond. Now we can calculate this through an equation for bond order. So bond order, quite simply, what bond order does, it represents the number of bonds between atoms. And to calculate bond order, all we do is we look at our molecular orbital diagram and we count our bonding electrons. So these are in our sigma and pi bonding orbitals. Next, we subtract our non-bonding or anti-bonding electrons. And what orbitals are we looking at for anti-bonding? Anti-bonding? So instead of sigma and pi, it would be sigma star and pi star. Okay. So from this equation, we're going to figure out the number of bonds between our atoms. Okay? And if the bond order is 0, then there's no bond and the molecule is not stable enough to exist. There's no bond between atoms. We don't have a bond. So for our last question for today, and we'll work on this one together, let's take a look at nitrogen monoxide, NO, and let's try to get a sense of our bond order. So let's count together how many total electrons do we see in our bonding orbitals, our sigma and pi orbitals? How many total electrons do we see in our sigma and pi orbitals?
Can we count the 2s on both floors?
Yes, yes.
And I got 8.
8. Yep, exactly. 2, 4, 6, 8. So we have 8 bonding electrons. 8 bonding electrons. And from that, we're going to subtract the number of anti-bonding electrons. And how many total anti-bonding electrons do we have in our sigma star and pi star? 3. So we have 3 anti-bonding. Okay, we then divide by 2, and that gives us a bond order of 5/2 or 2.5. Now, the real beauty of MO theory is it can describe the amount of electron density shared between atoms in terms that the Lewis model cannot, right? How do I describe a 2.5 bond? I don't have the tools in a Lewis structure to do that, right? When we describe nitrogen monoxide, we are limited when we think about it from just the Lewis structure perspective. Using the MO theory model, we can now explain that this amount of electron density shared between our nitrogen and oxygen atoms is not quite a double bond. It's stronger than a double bond. We have more electron density shared, right? We have a 2.5 bond. But is it a triple bond? Is it quite there to be considered a triple bond? No. So that's the real strength of MO theory. And the main way that we use MO theory in this class is when we start to describe pi systems in resonance and aromatic systems. We will not draw a ton of these diagrams, but it's important for you to understand how they work in terms of calculating bond order. Does that make sense to everyone? So if given an MO diagram, you should be able to tell me the bond order. That's what I'm expecting of you.
So we're not expected to draw like.
Not from scratch, not from scratch. Yes?
So we should always expect the bond order to be about 3 or less for a triple bond or
For the majority of molecules, you'll see the bond order will be 3 or less. Yes. Okay, and we'll continue on next class session.